Hello, I hope you're doing great and getting used to online labs. So this week we will be working on Lab 9, Magnetic Poles and Fields. So before I getting to introduce you to the simulator, I'll go over the concept of magnets. So in this video, you will learn about the basic concepts of magnets, and it will help you to answer the lab report questions. Well, so we all heard about magnets. Basically, we can divide the magnets into two categories, permanent magnets and electromagnets. So what are permanent magnets and what are electromagnets? So electromagnets are materials that we can magnetize by using electricity. So basically, when you have a coil like this one, and if you connect it to a battery or a power supply, you can make this coil magnetize. So those are electromagnets because it's powered by the electricity, right? And then the permanent magnets. So permanent magnets are the materials that keep a permanent magnetism in this material. So we don't need electricity to power up permanent magnets. They are magnetic by nature, right? Well, there are a lot of applications of magnets. Just to give an example, so permanent magnets are the magnets that you're using in the refrigerator, right? Just for the decorations. So that's one example of permanent magnet. And the metal detectors, those are electromagnets. So where we get a chance to control the magnetic power, and also we can switch on and off the magnetic power, right? So the metal detector is one example of electromagnets. So there are advantages and disadvantages of both magnets. So electromagnets, we should be able to control the magnetic strength, right? So that is a great advantage. So if we need it, you switch it on. If you don't need it, you can switch it off. And also you can maintain the strength of the magnet. So wherever you need to apply a strong magnetic field, you can use electromagnets. Then permanent magnets, they are working without a power supply. So it is portable and it is energy efficient as well, because you don't need power supplier to activate permanent magnets. And also these permanent magnets are comes in various dimensions. So there are small magnets and also huge magnets, but depending on where you want it, what type of magnets you need, the permanent magnets are available in different dimensions. Then the disadvantage of electromagnets. So we need coil to make a magnet, and also it need to be, if you need a strong magnet, then you need a significant amount of coils. And also we need a power supply, right? And also we need to supply that current using a coil or a wire. So we need to find a suitable wires to make these electromagnets. So it is little difficult to create electromagnets. But also there are disadvantage of permanent magnets as well. If you heat up these permanent magnets, it loses its magnetism. So we cannot use permanent magnets in a hot environment. So we cannot apply it in a warm environmental applications. Then the fixed magnets can pull anything towards it. So it is not flexible to use anywhere. But electromagnet, there's a flexibility that you can control the strength of magnetic strength, I mean. All right, so the magnetic field. So if you think about a permanent magnet, I believe you all have seen a magnet. So there are in a magnet, you can find a north pole and a south pole. And if you use a iron powder around a permanent magnet, those iron powder are really tiny and they will arrange in this fashion. So you will be seeing this nice order of iron powder that distributed around the permanent magnet. And if we keep the compass around it, you will notice that the north pole of the compass is pointing towards the south pole of the magnet. Okay, so in a magnet, there's a magnetic field around it, and this magnetic field is a vector. So you can find the direction of this magnetic field by using the compasses. So wherever the compass is directing is the direction of magnetic field. So in the lab, we were supposed to use a couple of compasses and keep it around a permanent magnet and track the magnetic field lines. So you will be seeing another video following this one with a little activity that we did, like throwing out a bunch of compasses around a permanent magnet, and you will be seeing like how those the compasses are arranged around the permanent magnet. Right? So please use that to answer the questions on pre-lab on the lab manual. Then, so if you look at it closely, you'll be seeing that the magnetic field lines are starting from North Pole and it travels toward the South Pole, like in this picture. Now, if you keep a couple of magnets close to each other, these magnetic field lines cannot cross each other, but they can add or subtract each other depending on which direction they go. So if you keep a North Pole and a North Pole together, I know it is hard because North poles are repelling each other, but somehow if you keep the North Pole and North Pole together, then the number of magnetic field lines that's around the magnet will be doubled. So the strength of the magnet will increase, right? So again, so if you have this magnet, like in this picture, so here if you count the magnetic field lines that's going from the North Pole, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 field lines are going around from the North Pole in this magnet. So if you keep another identical magnet on top of this one, having North Pole aligned to each other, then the number of field lines will double. So it will be 22 field lines instead of 11. So you basically you can make the magnetic strength increase by using a bunch of magnets together. Now, if you keep a South Pole with the North Pole, then you can reduce the strength of the magnetic field. So when you're storing magnets, we basically store them having North and South Pole attract to each other and bundle it. Then the units to measure magnetic field is Tesla. So 1 Tesla is 1 Newton per am meters. Newton per am meter. So Tesla is a famous scientist who figured out that we can induce current by changing the magnetic field. So if you ever visited the Niagara Falls, you may have seen a huge statue of Tesla. So it's honoring him to about this theory. So in close to Niagara Falls city, they get powered up by the movement of that water in the Niagara Falls and generate electricity from that. Well, so there's a law called Faraday's law. So the Faraday found out that we can induce electromagnetic field, that means a voltage in a circuit, by changing the flux over the time. So what is flux? Flux is the basically the let's say number of field lines that going around a coil, let's say. But anyway, so the flux is the number of loops in a coil times the magnetic field times the area of the loop. So here we can induce a voltage by changing the flux over the time, right? So if you want to change the flux, if you look at this equation, it's NBA, right? So number of coils. So if we can change the number of coils, then we can induce a voltage. Also, we can change the magnetic field and induce a voltage. Then the third quantity is we can change the area of the loop and induce a current. So with regard to B and A, also we can change the angle between B and A and induce a current. So there are 3 quantities that we can change to induce a current in a circuit. So we call this process as the electromagnetic inductance, right? So basically when you are moving a magnet around a coil, now if you see, notice this picture. So there's a coil and it's connected to a meter, right? So there's no battery. But if you move this magnet around the coil, it will induce a current on the this detector. So that's called the electromagnetic induction, because you can change the magnetic field and induce a current on the circuit. Okay? So the important word is change in the magnetic field. If you are holding a magnet, it will not induce a current. But if you move the magnet, it will induce a current. So there should be a change in the magnetic field in order to induce a current on a circuit. So we will be using this simulator to work on the lab. So let me take you to the simulator, and then I'll talk about the options that are available on the simulator that you can use to work on the lab report. So when you open the simulator, there are options that you can go. So first we will go on to the bar magnet, and here, here's the bar magnet with North Pole and South Pole. This is a compass. Red indicate the North Pole, and the white color point indicate the South Pole. Over here, you can change the strength of the magnet. So if you want to make the permanent magnet very strong, you put it to 100%. And you can click on the show field. So it is showing the field lines around the magnet. And also let's use a compass so you can see where the compass is directing to. Right? See, North Pole is always seeking for a South Pole. Okay. So if you think about this scenario, now on Earth, there's a magnet, like huge magnet embedded in there, right? That's why we have a North Pole and a South Pole. So geographical North Pole, like if you're using a compass, the compass's North Pole is pointing towards the geographical North Pole of the Earth. So actually that is the magnetic South Pole on Earth. Okay. All right. So then the other option is we go to the pickup coil, and here we see a coil and a bulb and a magnet. Now here you can change the indicator. So you can change it to a bulb, or you can have a voltage indicator. Now here, when you move the magnet, you can see a current is inducing on the loop, which make the light bulb lit, right? Now, when you hold the magnet, it won't light up, but when I move the magnet, it's lights up. So by changing the magnetic field, I can induce a current on the circuit. And also I can change the number of loops here, increase the loops, or also I'll keep the magnet here. So there's no induced current, but I can change the loop area. See, when I change the loop area, it's also induce a current, right? And also you can change the number of turns. When you change the number of turns, it induces a current as well. So there's a change in any quantity, like number of loops, or the area, or the strength of the magnetic field can induce a current on the circuit. Well, we like to have a voltage indicator where we can observe the direction of induce. So when I'm bringing a North Pole towards the coil, the indicator is deflecting towards left, towards the negative side of the voltmeter. And when I drag it back, taking the North Pole away from the coil, the voltmeter indicator like deflected towards the positive side of the voltmeter, or to the right, right? And then in the third part of the lab, you will be using the generator. So as you see here, you can run the water here and make this magnet rotate. So basically, when the magnet is rotate, the magnetic field around the coil changes, and it will induce a current on the circuit, right? So by changing different factors, you can change the strength of the brightness of the bulb. So increase the water speed. So that way it changes the magnetic field really vigorously. That induces a current, right? And also you can change the loop area. Change the loop area, that will change the brightness of the bulb as well. And also you can change the number of loops in the coil. That way you can change the strength of the induced current as well. So basically you're going to use this generator option to complete the part 3 of the lab, to analyze like what are the quantities that we can use to change a magnetic field on around a loop and induce a current. All right, so I hope this will help you to complete the lab report and understand the concept. And I'll see you next week. Thank you.